Our final scheduled speaker today. Here is Dr. Lari Koponen, at Duke University now. The floor is yours.
Okay, can you hear me now?
Yes, quite clearly.
Yeah, so kind of horrible to be the last person because now you all have already had a chance to tell what you have developed, and you will basically, I will have to admit to all the flaws that I'm doing worse than some of you. Like, for example, Rasmus said there's much nicer handling of the holes in meshes for designing coils. But basically, so my presentation is kind of filling in to some of the gaps that you saw, or like adding details to some of the gaps you saw in the last two presentations. So I've been here to tell basically about the method improvements for the optimization for coils for such designs as the meshes that Rasmus Tedder was showing for with his tools, and then Victor, of course, for the TMS application. So I can hopefully skip much of the explaining the application part. So TMS is also for our same as in with Victor, but I'll go slightly more into the detail of just how challenging it is in some aspects. So it is indeed brief pulses, but we need very high intensities. So we usually go well above 1 Tesla in peak fields, which means that the coil current in the windings is usually between 3,000 and 8,000 amperes at peak. And coil current density at higher end of input range actually can reach 1 kiloampere per square millimeter. Usually it's lower than that, between 100 and 500 amperes per square millimeter. But those all are like contributing to Joule heating, which is at ridiculous scale of 10 watts per cubic millimeter. So the basically only suitable material for sort of pulses like that is just going with copper, which has nice heat capacity, so that it heats limitedly during the pulse, and then cooling between pulses either by having there some thermal mass to keep stuff cool, or even with active cooling. So that is kind of the particular problem, but some of the tools are applicable to other problems too. So of course the optimization problem that Victor basically showed there was the energy efficiency. Rasmus also introduced and talked about the power efficiency. So basically these are energy efficiency, minimize inductance, power efficiency, minimize resistance for given stimulation field. Here we use E field, so induced electric field as our target, but it's just a linear map away from the magnetic field for these frequencies. So you can kind of omit that difference if you are actually designing coils for magnetic fields and not electric fields. It's just a matter of that our fields are slightly more hard to control for desired properties, and that's why our desired properties are slightly simpler than for those who design for magnetic fields. Here I'm introducing basically two methods to improve on the optimization. So one of them is by soon to be former colleague of mine, Luis Gomez, who joined there a few talks ago and asked questions also on people. And it's just turning again the problem around. So if the minimum energy and minimum power are solving using the quadratic constraints to make it solvable and unique, the problem, it's turning the problem again around, that we give distinct upper limits for inefficiency, so maximum amount of energy we can use, and find the best and for how large area we violate the constraint at. And then mine is just basically adding, making a more efficient solver for the quadratic problem, so that I can add much more constraints for desired structural properties. So basically two problems. The first one is actually solving quadratic problem as a linear problem with much more constraints, but it surprisingly works. So it's kind of useful way to linearize the quadratic parts, and the second one is just indeed an optimized solver where actually turning the problem into its canonical format requires roughly between 1.1 and 0.5% of the constraints that you would otherwise need. So our meshes are as with previous, except that our holes actually, in my case, move around with the optimization. So their location is not fixed in the beginning, but the location is defined by the coil properties. But that just adds one more step to the optimization. So if you start with how the constraints would be handled in the Victor's presentation for the E field, so we actually want to constrain electric field norm outside the focal region. And in 2D, so in the case of spherical symmetry, because we don't have the radial E field at all, it's just to make that convex constraint into a linear convex constraint, we just have to use a regular n-gon sampling. If you put 16 constraints, you get 1% error for that. So for each field point you want to constrain, you need 16 constraints. And if you do it in 3D, you need 162 constraints for the 1% error. That's from one of those papers that was also mentioned earlier by Victor, at least. But there, I can send the link if somebody wants that. And the coil parameterization for us is exactly the same. So we're just focusing on optimizing the optimization problem. First part is indeed by my colleague, and there we just try to form a different optimization problem around the same concept. So we want to actually minimize the volume in which we violate our constraints. So we have a strict constraint what we want, and then we are interested in what is the smallest volume in which we have to violate that constraint. And the constraint here is that we want to keep the electric field outside of target at less than half of that of the electric field in target. So this is a fairly similar optimization problem to most of yours, except that we don't aim for the best possible solution for homogeneity, because that of course requires infinite amount of energy and wouldn't be buildable. And the two first parts of this are exactly same as with the stuff Victor was discussing. And the third part actually is same as what Rasmus is doing with the spatial harmonics. And the fourth part is combining that with identifying which of those actually are most useful for any particular problem, not just using them in the order they appear, but rather linear mapping them to a different set of harmonics in actual sphere to identify which of them are actually the best n first that we need to pick those up. And so basically, if you compute for equivalent spherical coil, you can identify efficiency of every single mode, and you can then actually sort them by efficiency instead of sort them by their canonical order in the decomposition. But if we want to define then the region, so we cannot actually just optimize for the region. We need to introduce new variables into the concept. So we turn the problem into a binary optimization problem of identifying points at which we violate our constraints. And next slide. So this is formulation for optimizing the minimum area at which, or minimum volume at which we have to violate the constraints. So if you see my cursor, we basically turn the minimum energy or minimum power equivalently into power or energy below a fixed constraint, minimize the area, because each of these spans one area of where the binary variable needs to be triggered to accept the fact that we are violating the constraint, which we linearized as with we do with norm constraints. And with this formulation, to actually add the quadratic constraint here, it is added with another slack variable. So here you see the quadratic function. It can be approximated with a set of lines, so that true energy will be always smaller than the worst of the lines that is being hit. So we have an upper bound for the energy, and we actually will be able to optimize the linear problem here instead of the quadratic problem. The idea just works and computes fast, and the slowest part is actually the SVD for the 10,000 times 10,000 matrix in processing the inductance or power matrix. In our case, we used inductance matrix, but for there, and the optimization is actually surprisingly fast itself. this is the case for unlimited energy, so where the energy is being introduced higher and higher towards, and you actually see that there will be, for finite coil size, even with that, there will be a limit. And then if we limit the given energy, we can approach that limit. So these will converge to the limit of the previous slide in spread. There is a commercial coil. So we can roughly half the spread if we give some slack of our efficiency. So we can make twice as focal coil that actually still stimulates as deep. Because if you make traditionally more focal coil, as you can see back here, traditionally more focal coil will stimulate less deep. So it will actually not stimulate the same region underneath our target where the coil was at in the Victor's presentation, where you saw the animation. So we can actually make twice as focal coil, like properly twice as focal, instead of actually making it more superficial when it's more focal. Where we also here use the fact that we didn't actually use here a planar surface, but the triangles were spanned on a surface that is as tightly fitting as you can have for it to fit multiple separate subjects. So a representative set of all the human heads. And here is then making such coils, which again is something that people were discussing a lot earlier here. So it gets into a 3D printing domain and 2-layer coils. So basically the 2-layer coils there, we probably, they at Aalto now have developed 1.5-layer coils, should probably try to see if there is something on their side that they have spotted that we haven't yet, and try to copy those probably for higher efficiency, because the 2 layers here actually lose efficiency compared to 1 layer, but 1-layer coil cannot be realized because the current density gets too large in the coil windings for managing the heating. And then into printing coil formers, this is just the PLA printed coil former. It indeed works structurally. We have also tested it, but it was too large to be printed in one piece, which is also something that was discussed. And to that, I'll come to the next extra slides to show that. We just glued 2 halves together. That doesn't work, and we wouldn't recommend that. So tenon and mortise joint, which is not resistant to pulling, but pulling is with glue, is not ideal. But if you actually want to join 2 pieces, either go with the flange, classical flange joint and plastic or metal nuts, depending on your application, or then some other mechanical structure that actually holds stuff in place mechanically and not with glue. Otherwise, you will get pieces that will deform under both assembly and use. So don't just glue 3D printed parts together. They don't really form structurally solid parts with that, but rather they want to deform when you press in the wires. So summary, basically, for making more focal, turning quadratic problem and into a linear problem by linearizing it forcefully actually allows you to solve for a more complex problem that you cannot actually solve in a quadratic formulation, which might be also interesting for other applications. And that's kind of why I present this as this form in this workshop, and let much more into discussions than actually go into detail of how it works in a particular application. So that is in the paper link that was on that slide. I should probably have it also elsewhere, but also the project numbers will help find that there. And the other part, Victor mentioned, coils are loud, and they are loud to the extent where they do destroy themselves in high field MRI devices if they are not designed for that. So side effect of putting more than 100 joules in less than 100 microseconds. The total pulse 500 microseconds involves power times putting the energy in, taking it out. So putting 100 joules in less than 100 microseconds in means that the mean power is about megawatts, and the peak power is between 5 and 10 megawatts, depending on coil and intensity. As a side effect of that, we get micrometer scale displacements at kilohertz frequencies, which is meters per second, which makes sound pressures above 130 dB near the coil surface for the coil that is touching your head. It's not always ideal. So of course, we want to address that. And for that problem, we needed optimization that produces reasonable coils. We want to have coils where we can limit the current density explicitly in the coil so that we get windings that are not too dense anywhere. So, and we want to limit the minimum feature size, which we actually can limit by limiting the stream function values in the absolute scale so that we don't have too small a loop, because small loops do displace more than large loops. And those were something we found with structural model. So if we return to this again, if we had trivially canonicalized the problem here into the canonical form that Rasmus showed us, where each of these is turned into 16 for 2D because it's 2D constraints, and these are turned into 2 constraints, and these are turned into 16 per field point, the problem will be too numerically too difficult for any of the commercial solvers I have tried to even find a feasible solution because of numerical problems, despite I perfectly well knowing that that problem would have to have solution, because I would, even if I would constrain it looser than that, those constraints would ever be triggered by the solver without them existing. The existence of them makes the interior point methods not work and not fail in feasibility trigger. So we just needed to solve that. That was a part of a larger project. I will show just a streamlined project mapping of how I do. So that part is here, generate reasonable windings. Once reasonable windings, build a structural model, put it into COMSOL, simulate it. If it converges this location of the holes correctly, be happy. If not, generate coil model and go through this structural model and repeat and just table those. So I don't have full optimization of everything, but I needed the optimization within my course tabulation. For reasonable windings, basically, efficiency adequate, limited maximum field within the coil because forces are product of magnetic field and currents, and then limited current density because of same reasons. So those constraints were the hard ones, and that's actually fairly simple. So I just give the algorithm here. My own function is unfortunately mostly script type, so I won't be just putting a pull request to B field tools, not yet, but I might at some point. So start with an unconstrained problem or almost unconstrained problem, just constraint the first constraint that you need, the only equality constraint of the problem, solve it, find all violations for each violation, constraint with exactly one constraint. Question? Oh. And then this produces actually exactly minimum number of constraints needed to constrain the problem. And as the solution actually satisfies all constraints and is a local minimum for that constraint set, it also satisfies all the constraints of the actual problem and is a local minimum of actual problem. So it is the global optimum. So you can basically take your favorite solver and make it more powerful by optimizing the canonical, how you form the canonical form. So this is, I unfortunately give it only as an algorithm and not as a code, where the part by asterisk is important for the convergence. And if I go with the tolerance of 0.1% for the convergence, so 10 times higher than that of the 16 points, it takes, for my example, it took 9 iterations to converge, to apply constraint essentially in the large blob in the center, around each hole, in the edges. For smaller coils, in the edges, the constraints span in there, also in the domain. And it needed far less than 0.5% of actual number of constraints of the naive 0.1, which for this case, actually, for any of the commercial solvers I tried, didn't actually compute because they said that no feasible point found in the feasibility check for the system. And also my hole handling, it's ugly compared to Rasmus's, so I'm just doing it also iteratively with this solution, finding between which loops it will land up and then constraining it afterwards with the iterative solver. So that I would definitely change for the Rasmus method the moment I have time to do that. But so it just produces nice windings, and they, when combined with a coil, they do perform fairly well. So efficiency is measured farther to the right, the more efficient you are, and then how good it structurally is, which actually here is helped by the design, the acoustic design of the outer containment here. is measured by the lower you are, the better you are. And of course, decibels are logarithmic scale. So this means that there is less than 10% of the acoustic power than this one, which is an MRI coil, and less than 1% of the acoustic power of these coils, which are conventional TMS coils. So in linear scale, it looks like this, basically. But for other applications, if your quadratic solvers start to seem slow or start to produce erratic properties or just don't converge at all with your constraints, the algorithm described there on the other slide might help, because it basically eliminates most of the constraints actually of having to put them with the logarithmic penalty terms into the solver in the first place. And that's what I leave it to the workshop slide variant. So I don't go into our application, but I go into how we design coils. Questions?
So I was curious, are the wires that you typically, what gauge are they, and what are they made? Are they hollow? Are they solid core? What's
So the wires in this case, I'll have to go back to showing the wires here. Where was the mold, potting mold? Did I show the picture of the potting mold? Yeah, the small picture there. So the wires here are roughly 10 gauge AVG wire, but it's not just 10 gauge AVG wire. It is compressed Litch wire. So it consists of 70 individual 0.2 millimeter strands that each have the glass polymer coating on them. And on top of them, here we have 0.39 millimeters of FEP, because this coil will actually see up to 10 kilovolts between those two terminals. And to make it rigid, the potting material there is basically corundum filled epoxy. So it's one of the ceramic particles, similar to industrial sapphires. And that's a printed mold from laser sintered nylon in this case, with the wires clipping into the places where they should, and with least amount of material, so that the epoxy can fill everything, because epoxy is an order of, by factor of 4 or 5, even in vanilla epoxy is stiffer than the nylon.
I see. And I guess, yeah, nothing or very few things in that are very good at transporting heat.
The corundum is better at transporting heat than most metals. So the corundum filled epoxy, when it's to sagging point filled, that it actually acts as very good heat sink. So you could, in principle, cool it also from the top of that, or then you would have to mill grooves into this to put there either forced air to flow heat away from there, or then even just water cooling, because the heat will transfer into the back plate of the epoxy corundum mixture there, which actually is very good at transferring heat. So it heat sinks that heating.
Lari, I have a question.
Yeah.
What about placing the coil inside a vacuum chamber?
So
you think would be reasonable?
So yeah, if you can do a vacuum chamber where you mount the coil so that the coil mounting doesn't leak sound, it would be perfectly quiet, but you need medium to high vacuum to actually suppress the. So here, the attenuation from even this, but there being atmospheric pressure in that gap is on the order of 30 to 40 decibels. So you need to actually go to millibar scale. So you need to go to medium vacuum. And if you go to medium vacuum, you cannot have a thin plastic window like this, because it would be pulled into the coil, and of course then there would not be vacuum. So you would need to add the distance to the scalp and then power by factor of probably 4. So then it becomes a competition against whether you become too inefficient to actually stimulate or not. And then of course here, the reason for these 4 holes is that they are located which point this coil has minimum amount of displacement. and those are actually mechanically coupled to the externality because you need to mount the coil somewhere. So then those would become just a dominant point, and if you need 4 times more power in the coil, the leaking of the sound through the mounting might actually be already larger.
Yep.
It might even
Okay.
the lowest single narrowband sound frequency is most likely partially leaked through those, and then exciting this thin lid here.
Yeah, thanks.
Thanks for the talk, Lari. Really impressive work. So, for example, for this QTMS coil, will this see continued development, or is it kind of a proof of concept for now?
So now I actually yesterday, for the first time in 4 months, got to get back to lab, and every part you see in this coil here is to be still replaced with improved parts. So this is the results that I had that were supposed to be for a conference that was supposed to be in March, but well, then 2020 decided to intervene. So I have actually optimized next gen optimized of the windings and how to pot them. These 4 holes are no longer needed, so I can actually remove them and increase the efficiency by a few % on the windings, and which also will increase the stiffness of the potting because it won't have those mechanical compromises. I have a better design of this sound containing lid existing, and then a less bulky version of the outer sound containment in the manufacturing process pipeline. So I'll be still doing a next optimization gen, and then hopefully getting to actually do experiments in some time scale with humans.
And thank you, Larry. Thank you, all of our presenters, and thank you to, I don't know, the 40 of you who didn't present and came to learn from really a pretty incredible swath of work. I've recorded these, and I'll be posting the recording and slides, and like I said in the chat, any codes that the speakers share with me. And so keep your eye out. That'll take me a couple days to collate everything. In the meantime, I hope everyone has a lovely afternoon or evening, as the case may be. And I hope to see most of you at a conference at some point in the future when we're allowed to travel again.
All right.
Yeah, thanks a lot, Austin. Oh,
Yeah, thanks
have a nice evening there. Bye-bye.
for organizing this.
Bye now.
Yeah, thanks to Austin and everyone else. Great initiative, and nice to hear from you guys. Yeah, bye.
Yeah, thanks everyone.